The next thing we want to discuss is doing calculus problems with parametric equations. So far we've talked about the definition of these equations, and we've seen how to graph them. Now we want to go on and connect that with the things that we've been studying in calculus class. And the first example that I'd like to go through is finding a tangent line. So I've given a parametric curve here in this example, and we want to find the equation of the tangent line to the curve at the point where t is equal to pi over 4. What we've seen up to this point, one way we can approach a problem of this type is to draw a graph, and I did that here. So I let t go from 0 to pi over 2, and then I get the following curve in the plane when I go through those values. Now what we are asked to find in this example is what's going on at the point when t is pi over 4. I'll mark that point on the graph here. We're looking for the tangent line. It would be something like that. And notice that in this example, we have a smooth curve, so we do expect that it should have a tangent line. This looks like a differentiable function. The algebra that we're given, though that's different from what we've done before, we don't have a single formula like a function, y equals a function of x. A lot of the steps that we use are going to be similar to what we did in Calc 1 when we found the equation of a tangent line. So the first thing that we need to do, we're going to find the coordinates of the point where the tangent line meets the curve. Then we're going to find the slope. And for the last step, we use point-slope form to put the pieces together. And the answer that we get will be the equation of the tangent line. These are the steps that we're going to go through. Let's start out by taking a look at the first step in this problem. So I want to find the xy coordinates of the point where the tangent line meets the curve. In this problem, I'm given formulas that let me calculate those coordinates. So using the formulas for my problem, I started with the formula for x, and I plugged in the value t equals pi over 4. You can see the result here. It turns out that x is 2 root 2. I went through a similar set of steps using the formula that we were given for the y coordinate, and the result that I found was 8 root 2. This is how we do the first step in the problem. So we found the xy coordinates of the point where our tangent line meets the curve. You can see those coordinates here, and I went ahead and converted those square roots to a decimal. That's optional, but I think sometimes that's easier to graph. All right, that was the first step in our problem. Now we're going to go on and do step 2. I want to find the slope of the tangent line. And this step is what's new to us for this question. So we had a way to do this in Calc 1, but right now we're working with a parametric curve, and so we've got to adjust the way that we find the slope of the tangent line. Okay, first, we know that the tangent line is going to be the change in y over the change in x. But on this example, we don't have a formula relating those two variables directly. So instead, I'm going to look at how y is changing with regard to t, and I'm going to look at how x is changing with regard to t, and then I'm going to compare those two quantities, and that will give me the relationship between y and x. Look at what I have at the end of that last equation. Now those formulas that I'm working with there, that's something that we know how to find based on the parametric equations that we are given as part of the problem statement. All right, so I set up that fraction here. And again, this is the new idea in this lecture. This is the main thing that I'd like you to get out of the example that we're working on. All right, what I did next, I want to fill in the pieces of that formula. So to find dx dt, I took the function that we're using to define x, and I found its derivative. You can see that here. Then I went ahead and did the same thing for dy dt. Next, I'm going to take these results and plug them into the formula that we have for dy dx. I set up that formula here, and then I plugged in what we calculated on the last slide. The next thing I want to do is simplify this a little bit so I can cancel some common factors. And if you want, you can use a trig identity on that last expression. So this is the formula for dy dx. And we want to find the value of this formula when t is equal to pi over 4. I set that up here. There is the formula for dy dx that I found on my last slide. And then we're going to set t equal to pi over 4. I did that here. And the next thing to do, evaluate those trig functions. Simplify. And it turns out that the slope of the tangent line is minus 4. That was the end of the second step. To finish up the problem, we're going to do something that's familiar. We want to use point slope form to write the equation of the tangent line. We found all the information that we needed on the first two steps. So there's the slope, there's the point. And to finish this problem, this is really just a high school algebra problem. We take our point slope form and plug in the values that we found for this specific example. Now, if we want to, we can take this last line and rewrite this equation in y equals mx plus b form. I laid out the steps that you would go through here on this slide. If you want, go ahead and pause it and take a look at the details. Everything here should be a review from high school math. And so our final answer, after we get that y equals mx plus b form, we have the equation of the tangent line shown there. And if we wanted to write it using a decimal number, that would be another way I could express the same answer. Okay, that's the end of our example. This is how you find a tangent line to a parametric curve. I went ahead and graphed what I found on that last step. You can see the result here. Everything does check out. The tangent line looks like it's a good fit for our curve in this example. Okay, what I'd like you to do next is give this a try. I have an example for you to take a look at.